Jump right in. Have you ever really thought about the invisible rules that run, well, everything? I mean, from giant planets spinning around the sun to just driving your car. Today, we're going to open up the universe's rulebook. So, picture this. You hop in your car, you put your coffee on the dashboard, you pull away from the curb, nice and easy, and nothing happens. That cup just sits there like it's no big deal. But then, bam, a squirrel darts out and you slam on the brakes. All of a sudden, your coffee cup becomes a projectile, right? It just lunges forward. What is going on there? It's not some weird magic, I promise. It's just physics. And the guy who finally cracked this code? Sir Isaac Newton. You see, back in the 17th century, he did something that was totally revolutionary. He stopped trying to explain why things move and instead gave us the math to describe exactly how they move. He laid out 3 laws that became the absolute foundation of physics. Now, before we can get into his laws, we've got to get to know the main character in this whole story, force. So what even is a force? Super simple, it's a push or a pull. But look at that key word on the slide, unopposed. See, if all the forces on an object are balanced, like pushing and pulling equally from all sides, then nothing changes. But when a force is unbalanced, oh, that's when the magic happens. That's when things start to speed up, slow down, or change direction. Which brings us perfectly to the first law. I like to call this one the stubbornness principle, because honestly, it's all about how much objects just hate to change what they're doing. So Newton's version sounds a little more formal, but here's the deal. An object that's not moving wants to stay not moving. And an object that is moving, it wants to keep moving at the exact same speed in the exact same direction. It's just going to keep doing its thing forever, unless some outside unbalanced force comes along and messes it up. And this stubbornness has a scientific name, inertia. You've got inertia of rest. That's what pushes you back in your seat when the car suddenly floors it. Then there's inertia of motion. That's your coffee cup wanting to keep going forward when the car suddenly stops. And yep, there's even inertia of direction. That's the feeling of being pulled to the side when your car takes a really sharp turn. Okay, so law number 1 tells us that you need a force to change motion. Cool. But the second law, this is where Newton basically gives us superpowers. It tells us exactly how much things will change. We're moving from just watching to actually predicting. And it all comes down to this incredibly elegant, unbelievably powerful little equation. Force equals mass times acceleration. F equals ma. That's it. 3 little letters that basically run the entire universe. It's kind of mind-blowing. Let's break it down real quick. F is the net force. That's the final overall push or pull once you add everything up. M is for mass, which is just a fancy way of saying how much stuff an object is made of. And A is for acceleration, which just means any change in how fast it's going or what direction it's headed. So what this formula is really telling us is 2 super intuitive things. 1, the harder you push something, the faster it speeds up. More force equals more acceleration. Makes sense. And 2, for that same push, a heavier object won't speed up as much. More mass means less acceleration. I mean, it's way easier to get a tennis ball going than a bowling ball, right? Well, now you know why. F equals ma. All right, on to the third and final law. I call this one the Great Pushback. And it's all about a simple cosmic truth. Forces are never lonely. The idea is so profound, but so simple. For every single action or force, there is an equal and opposite reaction or force. They always, always, always come in pairs. No exceptions. And you see this everywhere. Look at these examples. A rocket shoves hot gas down. That's the action. In return, the gas shoves the rocket up with the exact same amount of force. That's the reaction. You kick a soccer ball, and yeah, you're putting a force on the ball. But guess what? The ball is putting an equal force right back on your foot. You can feel it. It's a perfect universal symmetry. So you take these 3 incredible laws, you mix them all together. What do you get? What happens when an object's stubbornness, its inertia, gets combined with a certain amount of force? Well, you get one of the most powerful concepts in all of physics, momentum. Momentum, at its core, is just mass in motion. We figure it out by multiplying an object's mass by its velocity. A good way to think about it is, it's a measure of how hard it is to stop something that's moving. A massive truck lumbering down the highway has way, way more momentum than a kid on a skateboard, even if they're going the same speed. And here is the really beautiful part that flows directly from Newton's laws. In any kind of interaction, say two things bumping into each other, the total amount of momentum you started with is the exact same amount you end with. It is conserved. It might get passed from one object to another, but it never ever just disappears into thin air. And here's the math that proves it. All it's saying is that the total momentum of everything before a collision has to equal the total momentum of everything after the collision. This right here is why a game of pole works. The momentum from the cue stick goes to the cue ball, which then passes it along to the other balls. It's just a giant, elegant transfer of energy. So you see, Newton's laws aren't just some dusty old equations. They are literally the operating system for our reality. For more than 200 years, they described everything from that coffee cup on your dashboard to the paths of distant galaxies. They even paved the way for Einstein himself. So the only question left is, now that you know the rules, where are you going to see them running the show today?